Welcome to another video for General Science. In this video we're going to be discussing forces. Okay? So here are some of the objectives that we're going to discuss. The first two will be in this video. How do forces affect the motion of an object? And what are the four main types of friction? The next three topics will be discussed in the second video. Okay? Just to keep these at a respectable length. So how do forces affect the motion of an object? So let's look at the definition that you'll find in your text. A force can cause a resting object to move, or it can accelerate a moving object by changing the object's speed or direction. So here's a classic example of force being applied on an object, and that object being the man in that yellow the raincoat. You notice that the wind is applying a force to him, and it's changing his direction, or at least it's almost changing his direction. You can tell it's a pretty strong wind. Also, it's changing his speed. Depending on where the wind is blowing, it can be speeding him up if it's a tailwind, or if it's a headwind, which is a wind that's going in the opposite direction that he's moving, it's changing his speed. It's slowing him down. So this is a classic example of how a force can change the motion, or how it affects the motion of an object. Here's another example of a man that you're about to see get tackled. Okay, he's going to get tackled, and you're going to see that his direction is going to be changed immediately. So that was a large force. So football provides us with many examples of forces and how they change. So you'll notice that the running back's direction was changed, and the faster that your direction is changed, the more force that was applied, and the more painful that can be. So you'll notice that he tried to run into the end zone, but he was almost stopped by the defensive men. Okay, so in this example also is another example of force, but this is measuring force. You're going to notice some arrows that are pointing down. Those arrows indicate the direction of the force. Those are vectors, and we'll be exploring those directional arrows in more detail in just a few moments. But just notice how they're pointing down, because when you apply an object to a scale, okay, you're applying a force against that scale, and that's what's causing the measurement. So every time you weigh something at a market, okay, again, the arrows are pointing down, gravity is pushing it down. So every time you measure something at a market, you measure the force. You're measuring the amount of force that the item is applying to the scale. And the more that you apply to the scale, okay, the more force you're applying to it. So you'll notice I'm pouring more in. That's causing a greater force on the scale, causing the mass to go up. So what units do we measure force in? Okay, we measure force in something called newtons. This is named after Isaac Newton, who refined this idea of forces and moving objects. The best way to describe a newton would be to look at Isaac Newton's second law of motion, which is force equals mass times acceleration. And if you think about it, it actually makes a lot of sense, because we're talking about moving objects here. Objects typically have a mass, okay, and that mass is measured in kilograms. So if they're a moving object, then they also have an acceleration, and acceleration is measured in meters per second squared. So a newton is a combination of an object's mass times its acceleration towards another object. So kilograms times meter per second squared is our unit for a newton. Okay, so just a summary, our forces will be measured in newtons, and we'll signify those or represent those by using arrows. Alright, so here you have an example of a tug of war here. And you'll notice that when I press go, nothing is happening, okay? Because we have a balanced force. You'll notice here that our red figure is tugging in the right direction, our right force, at a rate of 50 newtons, or at a force of 50 newtons. And our left force is tugging at a rate also of 50 newtons. So they're pulling in opposite directions with the same amount of force. This is a balanced force. So our sum forces is 0. That means there is no movement, because they are pulling at an equal amount, at an equal magnitude. Now what happens when I add another figure in on the blue? When I add this figure in on the blue, you're going to notice that my directional arrow is now greater. It is longer. It's at 100 newtons, my left force is. So my sum force is 100 minus the 50 from my red, okay, causing a pull to the left. Now I'm going to create, oh, the blue already won. Well, here, let me return this, and let's see what happens now. This red figure here, okay, is going to be pulling at a rate of 100 newtons. Plus the 50 is going to add up to 150 in the right direction. and my two smaller guys are going to pull at 100 force on the left, giving me a sum force of 50 newtons to the right. Now see what happens. So you're going to notice that our tray here is moving to the right. So now let me add another blue here. So now you're noticing that the sum force is 100 newtons to the left. This is an unbalanced force. So you're seeing the object move. Anytime we have an unbalanced force, I'm going to pause this. Anytime that we have an unbalanced force, you're going to have an object being moved. Okay? So when you have balanced forces, objects don't move because the sum of them is 0. Okay? So that's an example of balanced forces and unbalanced forces, or subtracting forces. Subtracting forces, let me return here. Subtracting forces means that since they're pulling in opposite directions, I'm going to subtract the two forces. So my left force is 250 minus the opposing force at 150 newtons to the right. 250 minus 150 is a sum of 100 newtons to my left. Okay, those are subtracting forces. Now, if I'm adding a force, let me return this. Okay, let me move this guy back here. So going back to my original problem, you see that I'm moving to the right. So if I add another force on my left side, I am adding a force. Okay, I'm adding a force causing more imbalance, and it's now tilting over to the left side. Okay, but when there are equal forces, okay, my equal and balanced forces, then I have a sum of 0, and I have no motion of the object. Okay? All right, let's go and discuss frictional forces now. Okay, so the first type of friction that we're going to discuss is static friction. Static friction is a friction force that acts on an object that is not moving. Okay, static friction always acts in the direction opposite to that of the applied force. So for example, I'm applying a force to the right. I'm trying to push my refrigerator to the right, but the frictional force, static friction, is applying its force to the left. So it's opposite to my applied force. Okay? And that frictional force is strong enough to oppose my applied force, thus I get no movement on the object. In fact, I can push the other way, and you'll notice that my frictional force is still applying its force in the opposite direction. So where is that force coming from exactly? Well, if I zoom in on the refrigerator, I'm going to be able to notice that the full surface of the refrigerator is in contact with my floor space here. Oops. Is in contact with my floor space. This frictional force is a microscopic force of the atoms of the refrigerator that are kind of mountainous in shape. The refrigerator might look smooth, but if I zoom in with a microscope, I actually see tiny little microscopic ridges that latch on to the microscopic ridges of my floor space. So even if I have a wood floor, it's still on the surface it might look smooth, but microscopically it's very, very rough. And it's kind of like two mountain tops kind of rubbing together. They end up locking up and causing a no movement situation. Okay, so this frictional force, as far as the refrigerator is concerned, is just enough to offset my applied force, so I get no movement. Okay, so here, let's take a look here. I'm applying 500 newtons of force, as you can see, and I get no movement. Now, what happens when I start to apply what's called a rolling friction? Let's go to that real quick. Here, let me reset this. So let me put my refrigerator now on a skateboard. Okay, now before I get this moving, notice here that my rolling friction situation is much different than my static friction, because now I have less contact. I have less contact with the floor. My wheels are in contact with it. This is called rolling friction. Okay, it's the frictional force that acts on a rolling object. This frictional force is actually anywhere from 100 to 1,000 times less than your sliding force or your static force. Okay, now notice, when my refrigerator was in full contact with the floor, not even 500 newtons would move the refrigerator. But now, as little as 55 newtons, I'm able to get movement. Okay, this is why movers use dollies and use other mechanisms to move heavy furniture, because those dollies, those wheels, create less contact with the surface, which requires you to apply much less force or to do less work on an object. Okay, so this is my rolling friction. All right, so let me go back now and let's talk about your static friction. So we discussed static friction in the sense that for a refrigerator anyways, it applies just enough force for me not to create any movement. But let's say I'm moving an object that doesn't have as much mass as my refrigerator. Now you'll notice that my crate also has static friction, okay? So at this point, I'm applying, here let me go into positive so it doesn't confuse things. I'm applying 94 newtons. 94 newtons of applied force is not enough to overcome my frictional force on my crate. So I'm going to keep increasing my applied force. Oh, and you'll notice now that I'm getting movement. So 130 newtons was enough to overcome my frictional force. In fact, let's find out how much exactly my frictional force was. Oh, let's get our values here. Okay. All right, let's see here. We are at 80, 94. Still no movement. All right, so now you see the sum forces to the right is 31 newtons. So my frictional force, if you look at my red arrow, is 94 newtons. I'm applying 146 newtons of applied force, giving me a sum force of 52. Okay? So my sum forces is to the right, causing me to move. So this is a sliding friction. So as soon as I overcome the static friction of an object, I now convert it to sliding friction. Now there's still friction there. Okay, I am still working, I am still sweating while I'm moving things, but now at least I have overcome my static friction and I have my object that is moving. Okay? All right, that does it. Okay, so that's your three frictions, your rolling friction, static friction, okay, and your sliding friction. Okay, good luck in your studying now.